we can do this kind of experiments, just do the code and then check the time. But the problem is difficult implementation. If the algorithm is simple, then yeah, there will be no problem. But if the algorithm is very complex, and yeah, if you have difficulties on the implementation, then it's very difficult to get the time. So in my research, so the algorithms run like 3 days. So it is impossible to wait for 3 days to check the running time. And there's also some kind of parameters. The results may not indicative of the running time on other inputs which are not included in the experiment. So some of the algorithms, they require some external parameters. So if you are dealing with the data science or if you are learning the machine learning stuff, so there are some parameters that you need to define. So if your parameter definition is not correct, then it will affect to the experiment results. The other thing is the computer specification. So in order to compare two algorithms, the same hardware and software environment must be used. So let's say you have 4 members in your team. Member number 1, member number 2, member number 3, member number 4. And each of you write the algorithm. Algorithm A, algorithm B, algorithm C, algorithm D. And then you run the algorithm in your laptop. Let's say, okay, the student number 1 and student number 2 has the newest laptop. Okay. And then the student number 3 and the student number 4, they use desktop. Then the performance will be different. So you need to run in the same environment, in the same computer to get the same result. That's why there's the theoretical analysis. People try to develop the theoretical analysis. What is the meaning by the theoretical analysis? It is a high-level description. Okay. So we are not going to implement, but we are going to look at the high level or the code. So we use the high-level description of the algorithm instead of implementation. And we will use running time function. So it characterizes the running time as a function of the input size. And it depends on the input characteristics. So it takes into account all possible inputs. So if you look at the input as a list, it will be different when you look at your input as a dictionary. If you have the input as a tuple, it will be different when you want to use another kind of input, which is set. Okay, so different kind of input will give you also different results. But when we use the theoretical analysis, we can just consider the input characteristics with these following data types. And the algorithm analysis, it is just for the algorithm, not the software analysis. So it means it allows us to evaluate the speed of an algorithm independent of the hardware or software environment. So if we use the theoretical analysis, we do not care whether you have the newest laptop or whether you have the very good PC. Okay, we don't care about it because we just care about how many times the algorithm will run. So when we do with the theoretical analysis, we will learn about pseudocode. Pseudocode, we call it pseudocode. It is a high-level description of an algorithm. Yeah, we call it, it is more structured than the English. If you use English, you have the subject, and then you have the verb, you have the object. So it's the grammatical structure. But when we use the pseudocode, yeah, we just have another kind of structure, like the sequential structure. And it is less detailed than a program. Maybe in the program, you need to define all the things, but in the pseudocode, it will be less detailed. Preferred notation for describing algorithms. So maybe in some of the algorithm that I explained, we will use symbol like top, or maybe symbol like alpha, or symbol like beta. But you will not see this one in your code. And it hides the program design issues. So it does not care you use function, or it does not care you use object oriented. But I just want to check the pseudocode. So that's the meaning by the pseudocode. This is example. If you use the control flow like if, then, if you use the while do or repeat until for do, you can just use any kind of this control flow. And as Python, we use the indentation. So indentation means you will use something like this. Okay. There's a space inside if you finish the statement with the control flow. And then we will have the method declaration. So if you have your method, then you will define the method name, and then you will define the parameter. So when you have the method name and you have the parameters, you need to define also the input and the output. Okay. So when we call the method, we will call the method with the arguments or the parameters. If it contains the return value, yeah, you need to also express the return. And when you do the expression, usually we just use the very simple assignment, not the same assignment in code. For example, I want to assign A as B plus C. So it means I do not use the common assignment in the Python like A equals to B plus C. Okay, so this assignment, usually it will be in the pseudocode. Equality testing. So if you want to check whether A is equal to B plus C. So in the Python, you will use equal to check the equality between the left and the right. But in the pseudocode, usually we just use only one. Okay, this is the common use. And then, for some formula like exponent, maybe in the in Python, you will use like n star 2 to indicate it is exponent. But when you do with the pseudocode, you can just do with the common expression n power of 2. So you don't need to write in details like you write in Python. So we need to learn about some important functions. So there are 7 important functions. So this is the common functions in the algorithm analysis. The first is constant. Constant, this is 1. It means whenever you run your algorithm, it will be always constant whenever the amount of data increase. So it doesn't care with the amount of data, it will always have the same speed. It will always have the same number of operation, or it will have always the same time forms. Logarithmic. So logarithmic means log n. Logarithmic n. So here is the log n. We have the linear of n. N means when the data increase, the number of operation also increase at the rate of n. We have n log n. N log n means n multiplied by log n. So n log n is this. We have quadratic, which is n power of 2. Or yeah, we can have n multiplied by n. We have cubic, n power of 3. So n multiplied by n multiplied by n. And we have exponential. The exponential is 2 power n. So if you look at these 7 functions, so this is the lowest one, constant. And it grows bigger and bigger. We call this is log-log chart. Okay. This is the log-log chart. The slope of the line corresponds to the growth rate. It means when we have our algorithm, we want to have the very best algorithm. So this is the very best algorithm, O1. When the number of data increase, we want to have the time performance stable. But it is almost impossible to have this one. So if you have your algorithm, of course you will try to find the lowest number of operations. That will be the best. We need to understand how to calculate the operations based on it. So the basic computation performed by an algorithm is, we call it the primitive operations. And then it is identifiable in pseudocode. It is largely independent from the programming language. So we don't care whether you use Python, Java, C, C++, anything. But as long as you have the pseudocode, we can do the analysis. Exact definition is not important. So we will see later. And it is assumed that it takes a constant amount of time in the RAM model. So the example of the primitive operations are, we evaluate an expression. We assign a value to a variable. We index into an array. Calling a method. Written from a method. So we call this is the primitive operations. So let's see. If we have the primitive operation, how we can count? We call it counting. So we need to count how many operations that are available in the Python. So by looking at the Python code, we can count the primitive operation line by line. For example, this one. The line number 1, it is an assignment. A equals to 1. Line number 2, it is an assignment. B equals to 5. Line number 3, it is a control flow. So I want to check A is less than B or not. If it is true, then I will go to line number 4. Print A less than B. If it is false, then I will go here and then print A is greater than equal to B. So we can have this. We call this is the primitive operation, one operation. This is also another primitive operation, one operation. So based on this definition, assigning a value to a variable. So if we assign a value to a variable, it is primitive operation. And we call this is only one time. Okay, so one operation. And then we want to check. Okay. Checking this one is also one operation. Printing this one is also one operation. When we do this else, it is one operation. And if we print this one, it is also one operation. If we look at this, okay, actually we can have the best case. Okay, the best case actually we can have 4, because 1, 2, 3, and then we will check what is the condition. If this condition is right, then we will do this one, finish. Or if we have another option, we can have like 1, 2, 3, and then if it is not correct, we go here and then do here. So we can have like the best is 5. Okay. So let's say, yeah, I just wrote this best is 6. That's the best operation. But what is the worst operation? The worst operation, it means if we run everything, if we run all the lines, so we have the worst operation is 6 operations. Because the algorithms run with this number, okay, with just a constant number. So this algorithm is approximately will be constant, because we know the number is 1, 1, 1, 1, 1, and 1. Now we have another code. I have a variable prop equals to 1, and then I have a loop for I in range 5, and then prop equals to prop multiplied by I. At the end, I will print. So what about this operation? The first is one operation. What about this one? It will run until n operation, because it is a loop. So in this case, I will run 5 times. Okay, 0, 1, 2, 3, 4. It depends on this number. So I can say it depends on the n. This operation, it takes 2 kinds of operation. The first operation is assignment, and the other operation is multiplication. It means I can just say 2 operations for n times, because we have n operation for this loop. And at the end, we have only 1 operation. So if I look at this one, I can say with, if you add all those, 1, plus n plus 2n plus 1. 1 plus n plus 2n plus 1. So you will have 3n plus 2. So if you run this one, yeah, the worst and the best will be the same. 3n plus 2, 3n plus 2. In this case, I can say that the algorithm is approximately a linear. Why it is linear? Because it is n. You can look at the here. Linear means n. So there's another example to count the primitive operations. We have L1 or list number 1. And the list number 1 contains 1, 3, 5, 7, 9. I have A equals to L1 index U. I have B equals to L1 index 4. And then I have the condition again, like this. So what is the operation? For the first, actually the operation is only one time because we have only the assignment. We want to assign this list into this variable. This one operation. This one, we have two operations. Why? The first is the assignment, and the second is to get the value from L1. So there are two operations. Here P equals is one operation, and L1 for it is another operation to get the value in the index form. Here is one operation, here is one operation, here is one operation, here is one operation. So if you look at the total, so the total will be 8 operations. Because all are the numbers, so we can say that this algorithm is approximately constant. What about this? It's the same with the previous one. This operation is only one operation because it is to assign the list to a variable. And then this is also one operation, just as an assignment. And then for this one, yeah, it depends on the number of this element. So it means it depends on the n. And this operation contains two operations, assignment and the multiplication. And this is one operation. In this case, yeah, we have 3n plus 3. 1, 2, 3. And then, yeah, in this analysis, the algorithm is approximately linear. You can look at this. I give you the Python tutor. This is a website. And it's very good website to check the line by line of your code. So for example, I have this. So let's start the coding by Python. And then if you look at this code, you can visualize the execution. So you can see one by one. And if you look at this one, there are 5 steps. 1, and then next is the assignment, next is another assignment, and then next is checking this condition. So this will be the case and case. Okay. Now, if I add more numbers here, what about the exclusion? When I do the visualize again, the step is still fine, okay, because it is just an if. So if we go to next, we will do assignment, and then checking, and then if it is true, finish. Okay, so this is what we call as the constant. Now let's look at this code. When we do visualize, there will be 14 steps. So we will do the assignment, one operation, and then this is another operation, and then I will do the loop. So you can see this A has the list 1, 3, 5, 7, 9, and the prop equals to 1. So if you run this, I now becomes 1, and then it will check again on the for loop. So now I equals to 3 because now it is in the index 1. Prop now equals to 3. So next I equals to 5. And prop now becomes 15. I now becomes 7. And prop becomes 105. And now I equals to 9. And prop now becomes 945. And last we finish by printing the prop and end. Okay. Now if I have more values, like this, then when I visualize, you will see the step is bigger. So we will do for every number. The I is 1, and then the I is 3, the I is 5, the I is 7, the I is 9, the I is 11, and so on. It means it follows the data here. So if the data is 10, then it will run n times, for 10 times. If the data is 20, then it will run 20 times. That's what we call as the n. Okay. So we have, let's see another operation. Suppose we have data in the list such that A is 1, 2, 7, 5, 4, 8, 3, 6, like this. And we want to find the maximum value among the elements. We want to call the function find max. So what is the algorithm analysis? You have this algorithm and you need to check line by line. So let's do it together. So I put this example. Yeah, these are the primitive operation examples. Of course, there might be some other kind of operations. So by inspecting the pseudocode, we can determine the maximum number of primitive operations executed by an algorithm. So I give you this. Line 1. So we can call the method and assign a value to a variable. Of course, if we want to call this method, okay, there will be one parameter. So yeah, we will call that one. And then next, yeah, we have the value assignment. This one is the value assignment. The value assignment will take two operations. This is the first operation, and this is the other operation. Line 4, assigning a value to a variable, indexing into array, and it repeats until n. So we have this assignment to n, okay, and value, it will be assigned to the data index 0 for the first time. Then this will be two operations. Okay. And then next is evaluating an expression. If value is bigger than the biggest is this one. So the value is two operations, then we can have like two operations multiplied by n. It will run for n times, and for every value, because it is 2n, 2 times 2 operation, then it will be 2 multiplied by n, because it is inside of the for loop. It will be repeating until n if the condition is true. So if it is true, then this will be n time. And the last one, just returning a method, so it's one operation. So in total, it will be something like this one. Okay. Two operation, to n, 0 until n, and 1. So if we want to check the best case, it means the best case is 0. If we want to check the worst case, then the worst case will be under n. So the best case is the condition is false. When the condition is false, it will never do this operation. The worst case is when every number is true. So we will do all the operations. So the best case, if we calculate this one, it will be for n plus 5. And if we have the worst, it is 5n plus 5. We have 2 plus 2 plus 1. We have 2n, and n. So if it is the best, we will not include the 0. If it is the worst, we will include n. That's why it is 5n plus 5. The best is 4n plus 5. So when we do the estimation with the running time, we can check with this kind of estimation. So the find max execute 5n plus 5 primitive operation in the worst case, and the for n plus 5 in the best case. So the easy way to see this one, if A is the time taken by the fastest primitive operation and B is the time taken by the slowest primitive operation, so the time t, okay, time t with the n variable or the n values, so I can make a kind of function like this. So this is the best case and this is the worst case. So this is how many times you want to take the operations, or how many times you want to do the method. And this is the number of the value or the number of the data that you want to check. So the time or the estimation running time will be in between the best and truest. So the running time will be Tn, is bounded by two linear functions. This is linear function and this is another linear function. So when we use this one, it will show the growth rate. It means changing the hardware or software environment, it will just affect the Tn. But it will not change the growth rate of Tn. So the number of data will increase, then the operation will be always between 4n plus 5 and 5n plus 5. Even though you run in the laptop or if you run in the PC, the growth rate will be the same. So the linear growth rate of the running time, Tn, is the intrinsic properties of the FindMax algorithm. So why the growth rate matters? Because if you have the data like this one, like you saw in the book before, if the data is small, then your time is small. If your data is big, let's say, you want to find the maximum value of the salary of people in Seoul. So how many population in Seoul? Maybe 8 million or 10 million? Maybe 8 million, because not all people have job. Okay, so let's say that 8 million. So you want to find the maximum from 8 million people. Then how many times do you need? So if you run the experiment, maybe it is very soon. So you can use this just time performance. If you use the log n, for the data 1, it is log 8. But for the data 2, it is log 8,000. If your running time is n, then you will have the 8 times for the data 1. If you use the data 2, it will be 8 million times. So you can see that the data matters. And if your algorithm runs in 2 power of n, of course, it will be very, very big amount of running time. So the best algorithm will be the smallest, or the log n algorithm. Okay, I think I will stop.